Good morning. Today we are going to talk about the efficiency and the mechanical advantage. Now, before we start, let's remember, how can machines help you to do work? Or help you do work, sorry. Does it change the amount of force or change the amount of work or the direction of the force or the distance that you are moving?
The distance?
What also? How the machine
changes the direction of the force and it can change the amount
of the work.
So it can change the amount of force, the direction of the force, and the distance that you are moving. These three things that can the machines help you. Now, in our real world machine, what is true about the work in compared to work output? In our real world, is the work input is greater than output, or the input equals the output, or the work that you inputted is less than the work that
work input equal work out. What?
This is ideal, but in our real world,
it's the work in is more than the work out because the efficiency is never 100%.
Yes, here in our ideal world, and this is cannot happen, the work input will be the same as the work output. But in our real world, the output is greater than the output.
Teacher, like you mean because we make a lot of work, then the result will be less than the work we did.
Yes, because there's a losses of energy that can happen in any system. So let's remember, what did we talk about the mechanical advantage? When we multiply, or we can say when we change the amount of force, when we change the direction of force, so we change the mechanical, or we have a mechanical advantage. The mechanical advantage, as we said before, it is an output force over the input force. Output force over the input force. As you see here, mechanical advantage, MA, is an output force over input. So in other, you can multiply them by cross product here. So you can say that, we can say that the first output, the output force that you get it in any system will be the mechanical advantage of the system times the force input. Or you can say that the force input will be the force output over the mechanical advantage. So I told you that the mechanical advantage is 1 or 0.5 as an example, and the force input is 20. So what's the force output will be? You have to multiply it. I say that this is 20, and the mechanical advantage is 0.5. So the work output will be 10 Newton. And so on, if I give you the first input, you can find the first output if you have the mechanical advantage.
Teacher, what is the unit of the mechanical advantage? Is it Newton square?
No, there's no unit. It is a Newton over Newton.
Oh, because it's ratio.
Okay. Now, you push down a lever with a force of 100 Newton to lift it as a 500 Newton. What is the input force? You push it with a 100 to lift a 500 Newton. So what's the input force will be? Is it 100 or 500?
500?
You push with 100.
No, it's 100.
It's 100, exactly. Now, you push down on a lever with a force of 100 to lift a 500 Newton box. What is the mechanical advantage here? The input force is 100.
Over 100.
Which is what?
50,000.
It is the output force over the input force. So it's 100 over 500 over 100, which is 5.
5.
So the answer here is 5.
It is equal.
This is the output force over the input force. Now let's talk about the ideal mechanical advantage. Ideal mechanical advantage is IMA. Now, the mechanical advantage of a machine is based on how the machine works in their real world. So in our machine, in our real world, the mechanical advantage, it's like the probability, or you can say it has to be, if it is an ideal, it is 1. If it is not ideal, it will be less than 1. So the ideal mechanical advantage, it means that it is a mechanical advantage, but it's not in our real world. Now, this is IMA, or ideal mechanical advantage. It is mean like there we have a mechanical advantage, but without losses, without heat. It could be without heat, without friction, without anything that makes you to lose the work output, which we called it IMA, or ideal mechanical advantage.
So teacher, if it's ideal and it's not in our life, so why we take it? Like, what is the benefit of taking it?
You have to know that the ideal, it's not in our real world, but you have to know what's the meaning of ideal in case to understand what's the meaning of our mechanical advantage in our real life.
Oh, okay.
I think we can also use it to compare how good the machine is.
Exactly. That's what we're going to talk about in efficiency here. So if you ignore that there's no friction, if you ignore that there's no losses of heat, of any type of energy, you have an ideal mechanical advantage. So if you have a lever now with a mechanical advantage of 6, so what is the more likely its ideal mechanical advantage? The ideal mechanical advantage, it is better than the mechanical advantage of our real world. So if it is 5, what is the ideal will be?
6.
Is it will be less than or equal or greater?
No, greater, 6.
Greater. So
Greater.
now, let's now talk about the efficiency. The efficiency, it's the measure of how much the work input is to the ratio of the work output to the work input, or you say the measure of how much work put into a machine is turned to a useful output work. The machine is a system, so you have a work input and you have a work that is output from the system. In this system here, you could have friction, you could have a heat losses, you have any type of or any other type of losses. So the work output cannot be as the same that the work that you inputted in the system. So that's why we have something we call it efficiency. We know that when we buy the machine, when it's new, its efficiency is 90%, as an example, or 95. Because if you put the work that is you add it, or you put it inside a system, inside a machine, is as an example 100 joule. But the output that's come out from the machine will be 95 because it's new. There's no heat losses. There's no something that is make up. Or we can say there's not some mistakes that you have it in the machine. No, but after few years, as an example, when you come back to use the machine, you will find that its efficiency is this none when you buy it. You find it as an example 60 or 50%. That's mean when you put 100 joule, you get 50 joule. So you lost 50 joule. Or if you have put a 100 joule, you get a 60 joule, so you lose 40 joule. You lost 40 joule. But at the beginning, when you buy it, when you put it as 100 joule, it gives you 95. You lost only 5 joules. So when you have greater efficiency, so you have a greater work output, you have a less amount of work that is lost. How to find out the efficiency? It is the work output over the work input. When I ask you the percent of efficiency, you tell me it is the work output over the work input by 100%. The mechanical advantage is different than the efficiency. The efficiency is a work output over the work input. But the mechanical advantage, it is force output over force input, or in distance input over distance output. And it could be greater than 1. such as we have on the pulleys. We say that the mechanical advantage is greater than 4 or greater than 2 or so on. But the efficiency, it must be less than 1. The efficiency is like the probability. The ideal of the things that happen impossible, we have this probability is 1. And here we have the efficiency. The ideal, in our ideal world, the efficiency will be 1. Or in ideal it is 1. In our real life, it will be less than 1. Is it clear?
Yeah.
Yes, teacher.
Yeah.
So, is it possible to have a machine with our real world with 110 efficiency?
No.
No. I told you the efficiency, it must be 1 or less than 1. So no. Now, as a percent, what is the efficiency of a machine that's put out 90 joule when you put in 100 joule? So from here,
So 90 over 100 multiplied by 100.
you put the work in is 100 here, and this is the in, and the out is 90. So it will be 90 over 100 times 100%, which is 90%. Now, which of the following machines loses the most energy to heat? Here now, as I told you, if you have now the machine, and this machine, it has an input and output. In the first case, we have 50% efficient machine. So what does it mean? That means if it is 50%, that means if you put on the system a 100 joule, so the output will be 50 joule because its efficiency is 50. In the second case here, we have an input with 100 and the output is 60. Now let's find the loss here. The loss here, it is 50, and the second one, the loss is 40. So which of the following lost the most energy? The first or the second one? The 50, exactly. Because I will tell, look here, 100 joule, the output is 50. So I told you, more efficient, less energy to lost. More efficient, less energy to lost. So the first one, it has 60. The first one 50, the second one 60. So the one that has most efficiency will be the second one, and the one that has less energy to lost will be the second one. Now, a machine efficiency can be improved by reducing friction. What can you do to reduce the friction in a machine?
Teacher, what do you mean about reducing the friction?
In our word here, I told you that if you have a system, or if you have a machine, sorry, or a system and so on, if you have now an input force and you have an output force, or input work, output work, you can say. So now for this one here, for this machine here, the input work, we know that it's greater than the output. Why? Because you enter the work with 500 joule and the output work will be 400 joule. So if you want now to graph it as like this here. So this is the input, the work input. Now the work output, most of them will be an output, and there's a losses. That if you add the amount of work for the output and the amount of work that is losses, and this work, it could be as come as energy like heat, or it could be losses because of friction. So this, if you add them here,